Now, the last speaker in the morning session is Peter Hammond. Peter is a postdoctoral researcher at Albert Einstein Institute, and his works includes binary neutron star and black hole neutron star mergers. And today we will be hearing higher order phase transition in binary neutron star mergers by him. Sorry for that. You can continue from that, Peter.
Okay, thank you for the introduction. Yeah, so I should first say that this work was done my previous postdoc while I was with the MP3M collaboration. So this was with some people at Penn State, New Hampshire, and a bunch of other people kind of around the world, but I am very thankful to my collaborators. And this work is mostly based on this paper here that's on the archive. Oh, everything just went black for me. Did the same happen for you?
Yes.
Okay.
Now everything fine, yes.
Everything is still fine? You can see?
Yeah, I can see, but I can also see something on top of your screen.
Yeah.
Like one.
The first one.
Yeah, in the first slide, maybe, yeah.
Yeah, I can't change the slide, which is strange. Sorry, bear with me a second. No, let me stop sharing and see what's going on. Sorry. Brilliant. Okay, yeah, so I'm going to be talking about phase transitions, specifically higher order phase transitions from baryonic to quark matter in binary neutron stars. So this problem has been studied a lot. We've had a lot of results in the literature now saying that phase transitions should show up at least in 3G detectors for gravitational waves from BNS mergers. But most, if not all of these works have focused on first order phase transitions. We have a very sharp change from one phase into the next. So we wanted to see how much of a difference there could be if we introduced a higher order phase transition, which implies a kind of smoother change from one regime into the other. So to do this, we started with three equations of state, so barotropic, so just density-dependent equations of state. These all have a first-order phase transition from hadrons to quarks. Two of them are based on chiral mean field methods, and one of them is a relativistic density functional. Just we wanted to kind of cover at least more than one base, just to show that this work is a little bit more general than just using one equation of state. And then what we do is we replace the phase transition with one of higher order. In principle, we can do this with any order, but for this work, we're going to be looking mostly on second and third order phase transitions. So second order phase transitions, basically your pressure is a function of baryon chemical potential is C1 smooth, and for third order phase transitions, it's C2 smooth. So percolation is basically this idea of removing a portion of the equation of state that you already have and replacing it with some polynomial that you choose. So basically you have freedom to choose a bunch of these parameters. By making different choices of these parameters, you can kind of fix the pressure at each side. And then using more and more, you can start to either fix the first derivative, the second derivative, either by matching at either side, or by imposing a value that you choose yourself. And we do both of these. So we are also going to focus just on choices of these parameters B that give us a higher maximum TOV mass of the equation of state. So typically when you start to add quarks into neutron star equations of state, you end up with a lower maximal mass. So we wanted to make sure that we were keeping as much of this maximal mass as we could. So all of the equations of state here give us at least a two solar mass TOV as the maximal mass, which is consistent with observations so far. So this is basically some results of what we get for these new equations of state. So in the dashed line is the original equation of state. This is for the CMF2 model. And then these colored lines are kind of the different percolations. So the numbers here denote the starting and ending densities of the percolation, and then the third, second, third is the order of the phase transition. So this is the kind of this pressure mu B plane is where we actually do the percolation. You can see that there's not very much difference here. But once you start taking derivatives of these things, so if you take the derivative of the pressure with respect to barochemical potential, you get the number density of baryons. You can start to see some differences here, but the real differences show up in the sound speed and this gamma, which is the adiabatic index, basically. So this, you can see for the original equation of state, this is a first order phase transition. So the sound speed goes identically to 0 over some energies. For the second order phase transition, you can see there's a jump in the sound speed, both at the beginning and the end of the percolation region. And for the third order phase transitions, you can see that the sound speed is continuous everywhere, but not necessarily smooth at the boundaries of the phase transition. So yeah, we have a few models. We have different numbers, different orders for different equations of state. We have a whole kind of zoo of these things. We can basically make whatever we want. We did make sure to respect causality for all of the equations of state that we ended up using. So you shouldn't see any sound speeds that are greater than 1. And then this is the final model. Obviously, you can see this one, things do start to get very nearly to C equals 1, but yeah, we do make sure that we respect causality. So things start to get a bit more interesting when you start looking at the mass radius curves for these equations of state, specifically because we start to see some crossing points. So you can see in the CMF2 model, these two equations of state kind of cross here, but you pick any two lines, they're going to cross somewhere. But here we actually have 4 equations of state that are all seem to be going through a very narrow region in this mass radius diagram. And similarly for the RDF model, we have kind of a few very nearby crossing points in this mass radius plot. And similarly for mass versus tidal deformability, we see these crossing points. So we basically have a bunch of different equations of state that all seem to share a mass and a tidal deformability for some choice of the mass, and the same for the radius. So I should say that this is an interesting thing to study if we start doing BNS mergers with these particular masses as our initial data, because the kind of leading order terms in the gravitational wave signal for the in-spiral are going to depend mostly on the mass and the tidal deformability. So if we just pick equal mass binaries and target these points for the different equations of state, we should see almost identical in-spirals, certainly up to anything we'd be able to measure with current detectors or maybe even future detectors. But because we have, different equations of state, we might possibly see some different behavior in the post-merger. So this is what we focus all of our simulations on. So to talk a bit about the simulation, so we use the code GR Athena++. This is based on Jim Stone's code Athena and Athena++, where we have basically taken that code, which only does GR in a fixed spacetime, and made it so that we can do dynamical spacetimes. So the kind of out of the box Athena++, we have this octree-based AML, which I'll talk about in a second, because I think this is one of the major differences between our code and many of the other ones, but kind of similar to a lot of other people. We use C4C for the spacetime. We use this Valenzo formulation for the GR and HD. Here we're using one-dimensional tabulated equations of state with the gamma law. This is just because percolation is barotropic. We don't know how to do this yet for finite temperature equations of state, but GR Athena++ is capable of doing finite temperature tables. So what does the refinement look like in Athena? So in Athena, we divide the grid up into a bunch of mesh blocks. Each of these mesh blocks has the same number of cells. So typically for our simulations, we use 16 cubed for our mesh blocks. Then when we want to do some refinement in some region, we divide that mesh block up into 8 smaller mesh blocks. So we, half the resolution in each direction and double the number of cells, and then we get 8 smaller mesh blocks, hence octree. You basically just keep doing this recursively. You just divide mesh blocks up and up and up until you hit the resolution you want in all the different regions. Then one of the advantages of this is that load balancing becomes very simple because each mesh block is exactly the same size. It should take about the same amount of time to do all the evolution on each mesh block. So simply by putting approximately the same number of mesh blocks per computational resource, we should get load balancing very close to equal everywhere. This does introduce a lot more communication. So each mesh block has its own ghost zones. So this means there's a lot of stuff that needs to be, the mesh blocks need to talk to each other. But we do something called Z ordering. So this, I will show a diagram of this in a second as well. Basically, this introduces some notion of locality to each mesh block. So a mesh block and its neighbors tend to end up on the same CPU thread or the same MPI thread, which means that the MPI communication that's actually required between the different mesh blocks is very significantly reduced. And most of this kind of ghost zone or this grid to ghost zone communication takes place in the same memory space. So it's just mem copies, which are very quick compared to MPI. We also use a global, I should definitely say global, time step, which significantly reduces the complication of the communication and also the prolongation and restriction operators, because we don't need to do any of this strange time integration stuff between different resolution levels. So this is kind of this is a blast wave problem, but this is kind of showing the mesh block structure. So each square here these are not grid points, these are mesh blocks. So you can think of each of these representing, a 16 by 16 grid of cells. And then, we're in 2D here, so we end up dividing each larger mesh block into 4. And then again, we divide those, medium mesh blocks into 4. And this is kind of the structure of the refinement that we end up with. As you can see, this is we're very easily able to kind of target the resolution where we want it. You can kind of refine mostly kind of as much as you want in just different places, and this allows us to kind of reduce the amount of refinement that we need to do in there. Compared to like a box in box kind of thing where you'd basically have to just cover this whole thing with a finer refinement level. So Z ordering, basically the idea is that you kind of label your mesh blocks in order with this kind of space filling curve. And what this means then is that, the numbers shouldn't jump too much as you go from a mesh block to its neighbor. And as I say, this means that your mesh blocks have some notion of locality. So if you do your load balancing just by following the Z ordering curve and you kind of cut it somewhere, your mesh block should end up on the same thread as their neighbors, which means that the communication load is significantly reduced. So back to some simulation results. So this is the pressure and the density for one of these CMF7 equations of state. And what I've highlighted here with the dashed line is the beginning of the percolation region. So within this density contour, this is where you're going to have this kind of percolated equation of state. And so this is very shortly before collapse. This is kind of the last simulations snapshot that I have before this model collapses. And then this is a different model. So this was exactly the same the same masses for the initial neutron stars for the different equation of state. And this one, shortly before it collapses, you can actually see this solid contour is showing us that there's pure quark matter inside this region here. So we do access kind of all the regions of the equations of state that we have. So what do the waveforms look like? So this is kind of what we're interested in. So this is the 4 different simulations that we performed for the CMF7 model. The colors here correspond back to the curves we have here. So we have the blue, the orange, the red, and the purple. This green one doesn't go near this point, but these stars are all kind of targeting this point here where the crossing is. So you can see that as we would expect, the in-spiral waveforms look very similar. There are some small differences here, but the simulation doesn't start much longer before this plot does, so that's kind of why we see some differences there. But what we do see is that as we suggested might happen is some fairly significant differences in the post-merger waveform. So especially you can see the blue, red, and purple models, they all very promptly collapse to a black hole, whereas this orange model seems to live for at least a few, maybe a couple of milliseconds afterwards. And we can kind of see this in the spectra as well. They all follow each other up through merger, and then you kind of have this very early in-spiral, but then this very early post-merger is quite similar. But yeah, it really, you see that these ring downs just from the very prompt collapse to a black hole, and then this orange model has some structure to it. And then on this plot as well, I have the noise curves for A LIGO, ET, and some Cosmic Explorer model. What you can see here is that maybe you might just be able to see the post-merger for this one if it was close enough, but probably not. But with these future detectors, we should definitely be able to see the difference between these different models. So one way we can kind of quantify this difference is through the mismatch. So the mismatch is basically 1 minus the faithfulness, or whatever you want to call it. This has a lot of different names in the literature. But basically, you can just think of this overlap operator as just kind of some kind of dot product between the two spectra of the different waveforms, and basically you just have effectively A dot B over the square root of A squared times B squared. So this is just some kind of normalized dot product between the two waveform spectra, and then you take one minus that to get the difference between them. So for our calculations that I'm going to show in a second, we use the D model of the Einstein telescope. And additionally, we as we saw and as I stated, the in-spirals we expect to be very similar. So what we can do is, rather than running this frequency integral from 0 to infinity, we can start at some frequency and only consider frequencies higher than that, basically excluding the low frequency part, which is going to correspond to the in-spiral, just to focus on our post-merger part of the waveform. So this is just showing kind of how I picked that frequency for these simulations. So here is the amplitude envelope with some scaling applied to it. And then basically this dashed line is where the kind of maximum of that happens. So these waveforms were all actually kind of aligned in time and phase by minimizing the mismatch over the entire signal. So this is kind of roughly faithful to what you would do in a detector, because you would have much more in-spiral signal than we have here. So just by matching that in time, then you say, okay, so this is where the merger happens. So what frequency do I hit the merger? And in here, it's about 1.9 kilohertz is what I call our merger frequency. So this is the instantaneous frequency. So basically just the time derivative of the phase of the signals. So this is kind of this is a matrix of the pairwise mismatches in the post-merger between all the different signals. So simulation 4 here is the one that lives for a much longer time than the other ones, 3, 5, and 6. So you can see here that the mismatches here are actually very high for the post-merger signals. So to kind of put this in context, the target mismatch for the templates that are used in current LIGO searches are about 5%. Here we're talking about a mismatch of over 40%. So this is very obviously different compared to so this simulation is very obviously different compared to the other ones. We do see some small differences between The other simulations, 5 and 6, seem to be quite similar, but this simulation 3 is a little bit more different. So this blue curve is simulation 3, then you have 5 and 6 here. You can see that while the amplitudes are slightly different, the frequency difference between these two ring downs is actually quite small. This one's a little bit further away, and then obviously this orange one is completely different. So we can ask the question kind of, why do we see this? So here we have the adiabatic index. So this is tells us roughly how stiff the fluid is. As you kind of compress a fluid element, this kind of tells you how much more it's going to start pushing back against you. So this is the simulation that lives for a longer time. And you can see that there's quite a lot of matter up here at very high stiffnesses. So this is kind of a 2D histogram of the mass that each lives at a particular density and stiffness. And this is at a simulation time of 12 milliseconds. So this is maybe this is basically at the merger time, slightly after. But this is to compare to this simulation. So this is one of the ones that collapses very quickly. So this is why I picked 12 milliseconds, because this is just before this one collapses. And you can see here that actually the stiffness is almost all of the mass is below a gamma of 3. So just to kind of put those two side by side, you can see here that there's a lot more stiff matter, and the stiff matter is much more able to kind of stop the collapse to a black hole from happening. It's able to push back against this, and that's why we see that this model lives for a longer time than this one, even though this one is accessing higher densities at this time. So this is all I really had to talk about. So what we've done is we've replaced the first order phase transition in 3 different quark-hadron equations of state using this percolation technique so that we can do some higher order phase transitions. We performed some binary neutron star merger simulations with 10 of these different equations of state, where we're targeting a kind of crossing point in this mass lambda space. And what we see is that the n-spirals match closely as we would expect, because the masses and the lambdas are very similar. But there's a big difference in the kind of post-merger behavior between these simulations. So just very quickly to do some advertising. So as I said, these simulations were all performed with GR Athena++. So we have dynamical spacetimes based on the Z4C formulation. We have this octree-based AMR, kind of standard GRMHD, using this Athena-constrained transport for the magnetic fields, which I don't have in these simulations, but this is a very powerful tool. We have radiation coming online, kind of maybe not as we speak, but we're in the very kind of final stages of testing this now. And we're running some BNSs now with the M1. So hopefully there'll be some papers coming out on that soon. We can do various different equations of state, including these the standard composed tables in 3 dimensions, with the YE as well. Like many other people, our CTP is based on Wolfgang Castell's model, but we use a slightly modified version that we find works a bit better for the tabulated equations of state. And we also have this Athena K code coming online now. So as we've heard a lot the past couple of days, GPUs are basically becoming necessary in order to get computer time for running these big simulations. So Athena K has as of now, Athena K has a slightly reduced feature set compared to Athena++. We don't, with the radiation transport isn't quite as far along, but is in progress, shall we say, but everything else is pretty much there. So we can do, Z4C with the GR side. We have the same standard Valencia. formulation. One of the, I would say, the biggest advantages I've seen of Athena K is that we maintain, problem dependent 75 to 80% weak scaling on tens of thousands of GPUs. So we can effectively saturate the largest supercomputers on the planet with this code and still maintain a very high efficiency. And yeah, I realize I've gone through that a little bit quick, but that's everything I have.
Thank you very much, Peter. Very nice talk. I have seen some questions, and we will now move to the question part.